So these are some electric circuit sample problems. So here's the first problem. There are three resistors in parallel and they are connected to a 12-volt battery, and it's asking the following questions. So the first question is, what's the total equivalent resistance of this combination since they are in parallel? Just use the formula. And its second part is, what's the current through each resistors? And a simple circuit, something like that, you can just use the series and parallel combination and then just use the Ohm's law. And if the circuit gets complicated, we will see actually, then you will have to use Kirchhoff's law. So that's the main idea. So here first part is just finding the total equivalent resistance and just use the formula, right? So R equivalent for parallel combination is 1 over R1 plus 1 over R2 plus 1 over R3, and don't forget the reciprocal of that. That's the formula, right, for parallel combinations. And just put all the resistance values. This 1 over 70 plus 1 over 42 inverse, and then just use your calculator to do that, and you'll get it's 18 ohms. Okay, so the total equivalent resistance of this parallel combination is 18 ohms, and you can clearly see the parallel combination decreases, right, reduce the total resistance of the combination. Okay, part B is also easy. So now here first, this is the total current, right, that the battery drives, and that total current gets divided into three branches, right, because this is parallel combination. Depending on those resistance, let's say I1, I2 and I3 are the current through each resistors, and since this is parallel combination, each of these resistors are getting the same voltage, which is 12 volt, because you can clearly see, right, all these resistors are getting exactly same volt, which is 12 volt. And that's what happens in parallel combination. In parallel combination, the voltage across the resistors are same but different current. So since voltage is same everywhere, right? So then just use Ohm's law. So let me just quickly remind you Ohm's law. Ohm's law is V is IR, right? So current is V over R, and that's what we're going to use actually, right? So I1 is just V is same for all, which is 12 volt, divided by, but they have different resistance. So R1, so 12 divided by 58, so 0.21 amps. So similarly, you can do I2 is V over R2, and 12 divided by 70, that's going to get you 0.17 amp, and I3 is V over R3. V is 12 volt again, and 42 ohms, and then that's gonna get you 0.28 amp. So these are the current through each of these resistors, So that's how you solve this simple problem. So here's the next problem, and this is also you can just use series and parallel combination, to solve this problem. You may not require any Kirchhoff's. If you want, you can use Kirchhoff's law, but you can just use Ohm's law, series and parallel, Okay, here's the thing. So you have some unknown resistor R connected in series with 24 ohms resistor, and a voltmeter is connected across the second resistor, 24 ohm resistor, and it says it's recording 6 volts. So 6 volt is the voltage across 24. So obviously from common sense, right, so since this 9 volt gets divided into 2, if this is 6 voltage across 24, the rest of the volt, which is 3 volt, has to be right across across this unknown resistor. That's the first thing. Yeah. And one more thing is, since these two resistors are in series, the current must be same, right? Current must be same everywhere, because since there's no branch, and voltmeter has the ideal voltmeter has infinite resistance. It doesn't get any current. So current has to be same for both resistors. That's the main idea. So let's first figure out the total current through the circuit, which is same for both from the second data. So I has to be, right, V 2 over R2. So V2 is 6 volt divided by 24, right, is 1/4, is 0.25 amps, right. So that's the current through the circuit, which is the total current. Since they are connected in series, the current has to be same everywhere. Then for R, just use Ohm's law, right. We know the voltage across R is 3 ohms, 3 volts. So, and we already know the current, right, current is same everywhere, which is 0.25 amps. Then just use Ohm's law, right, V is I times R. So then R is acting the unknown resistance. R is V over I. So V is 3 volt and the current is 0.25. That's it. It's 12 ohms. So the resistance of this unknown resistor has to be, has to be 12 ohms. Or simply, actually, if you just want to use Kirchhoff's law, simply you can just do that, and it may be a lot easier. So but before you use Kirchhoff's law, you have to put all the minus and plus signs. This is minus, this is plus, and since current flows that way, this side must be positive, this side must be negative. Again, for the second resistor, same thing, this side must be positive, higher potential, this side must be negative. And then, so this is using alternate technique, using Kirchhoff's law, which we will do in detail next problems. If you just want to use Kirchhoff's law, that's fine. So around this loop, Kirchhoff's voltage law said the sum of the voltage around the loop has to be 0, right. So starting from here, so 9 volt, which is positive, because you are going from negative to positive, right, based on the rules. And here this voltage across this unknown resistor is negative I times R, right, and because you are going from positive to negative. Same thing for second. Current is same, I times resistance is 24, and sum of all this voltage has to be 0. That's it. And the current is now, and this whole thing is actually just 6 volt. This whole thing is 6 volt, right? And current is this. Current is 0.25. Then you can right away you can solve for resistance. So 9 minus current is 0.25, resistance minus 0.25, 24, right, is 0. This whole thing has to be 6, which is, and then your resistance is 9 minus this is 6, right, divided by 0.25. That's it. It's 3 over 0.25 and 12. So no matter what technique you use, you will end up with the same answer. So either circuits are simple, you can just use Ohm's law, series and parallel ideas, but when the circuit gets complicated, you will have to use Kirchhoff's law. So here's the next problem, which is used in photosensing device. So it says the photoresistor is connected in series with a 1 kilo ohm resistor, and it says the photoresistor its properties like that when light falls on the photoresistor, its resistance decreases. Okay, that's how it behaves. And it says on a sunny day, when light falls on this photoresistor, when light falls on it, the photoresistor's resistance is only half a ohm. It's almost 0. But at night, when light doesn't fall on it, its resistance is 25 kilo ohm. Okay, and the voltmeter is connected across the 1 kilo ohm resistor, right. And there are two questions. What does the voltmeter read, right, on a sunny day? So on a sunny day, right, so let's call this as R. R is the resistance of the photoresistor. R is very high, very small, only half of ohms, right. And it's asking what's the voltmeter resistance, this on sunny day. Okay, this is a fixed resistor, and it's the same idea, so current is same, right, because these two are in series. Current must be same everywhere. So let's first find out the total current. So total current is on sunny day is total voltage divided by total resistance, right, and total voltage is 9 volt. Total resistance is on sunny day, its resistance is only half ohms, and it is 1000, right. 1 kilo ohm is 1000. So 1000 plus half ohm is almost negligible, right. So everything is dominated by 1 kilo ohm, right. And then you can do this calculation. It's 9 divided by 1000.5 ohms, and it's 0.00899 amps. And the voltmeter reading is the voltage across, voltage across the 1 kilo ohm is the voltmeter reading, right? Okay, voltage across the 1 kilo ohm resistance is the voltmeter reading, and that's going to be just do I times R, Ohm's law, right? And I is 0.00899, right? And resistance of this resistor is 1 kilo. 1 kilo you must convert into ohms. 1 kilo ohm is 1000, right? Okay, that's going to be the voltmeter reading, right? So it's gonna read almost 9 volts. All the voltage it will record all, because, and that makes sense because this photoresistor almost conducts at sunny day, right? So all the voltage will be dropped here, right? So part B, at night. At night, this is on sunny day. This is the daytime, part 1. At night, the resistance of the photoresistor becomes 25 kilo ohms, okay, and that is 25,000 ohms, right? And let's figure out and that will change the total current. Now total current will be reduced, right, because its resistance has increased by many times. So what's the new total current? So again, V divided by R total. So what's going to be the total current? So total voltage is 9 volt, and the total resistance is going to be this plus this, because they are in series, right? And 25,000 plus 1000, so 26 kilo ohm, right? So 9 divided by 26,000, and this is going to be the new current. So the new current is this, and that is a very small current, 3.46 10 to the power -4 amps if you do that. And the new voltmeter reading, right, at night is just I times R. The new current is 3.46 10 to the power -4, and the resistance of this is still 1 kilo ohms, so 1000. So that's the new voltmeter reading at night. Okay, so I times R is 0.35 volt. Okay, so at night actually it doesn't even record, actually it's very little voltage, right? So this circuit can be used as a photosensor, a light detector, right? Okay, here's the next question, and it's a very important circuit actually in any electronic circuits you will see. It's called voltage divider circuit. So voltage divider circuit is basically two resistors like this in series, right, and a battery is connected, and if so the voltage is taken one of these resistors. Let's say the first part is what's the voltage across, what voltage do you expect across R2, and that's easy to calculate, right? And so because they are both these resistors are in series, right, the current must be same everywhere, right? Current is same in series, right, because there's no branch. So how do you find? So I is total voltage, which is the input voltage, divided by total resistance. Total resistance is R1 plus R2. So first you have to find the current, and current times R2 is the V out, voltage across R2. So it's 12 volt battery divided by R1 is 220 kilo ohms, right? So kilo ohms means 1000 plus second is 500,000. Or you can just keep it in kilo ohms and current will be in milliamps, or change everything into standard unit. So that's the current, right? So calculate that. So you can calculate this current, right? And so V2, which is voltage across, because it's acting this voltage across R2, is just I will be same times R2, Ohm's law. So I is this 12 divided by this whole thing, so 500. Now just use the R2 is 500,000, right? So that's your V2, So do this calculation real quick, and then you will see 8.33 volts. So that's the voltage you expect, right? So voltage across R2 will be 8.33 volt. Now the main problem is, how do you actually record the voltage in reality, right? In lab, in reality, you're going to need some kind of measurement device, right? We call voltmeter, right? We call voltmeter to measure something. So how do you measure? So you just put the voltage, voltmeter, right? So let me redraw the circuit again. So to measure the voltage across any resistor, you need a voltmeter, voltage measuring device, right? And the problem is the voltmeter will have some kind of internal resistance. It's not ideal, so you can replace by this, right? Voltmeter will always have some kind of internal resistance. Okay, its resistance ideally it should be very high, right? So it doesn't draw any current, but that won't be the case. It will always have some kind of resistance. It says the voltmeter internal resistance, also called impedance, is 900 kilo ohm. Okay, that's what it says. So now what's the voltmeter reading? What's the new reading, right? What's the V2 is the voltmeter reading, right? And because of its internal resistance, it won't actually, the voltmeter will not record exactly 8.33 volts. Okay, because the voltmeter will do some loading. It's called loading effect. It gets some current, it bias some current, and because of that, it will change the effective resistance. It will reduce the effective resistance between these two, and then it will record less than this, and that's called loading effect. This effect is called loading effect. So you have to be very careful, and you can't blindly depend on the voltmeter that you are recording. You have to see what scale you are using. Okay, so let's do that. So first you have to find the total current, right? Again, this is a 12 volt battery. So first R total, you have to find the R total. The total effective resistance here is R1 plus. So in the second, you have these two resistors in parallel, right? Because the voltmeter has some 900 kilo ohm of resistor, so that's why you have some plus. I'm gonna say R2 parallel with the voltmeter resistance. And how do you calculate? So R1 plus this is 1 over R2 plus 1 over R inverse, right? And let's put the values. R1 is 220 kilo. So let's do everything in kilo ohms. 1 over R2 is 500 kilo ohm plus 1 over the voltmeter has 900 kilo ohm square root, inverse. So the total effective resistance now has changed, right? And if you do that, so R total will be 541.4 kilo ohms if you do this calculation. Okay, about 541 kilo ohms. Okay, that's the total. And then you can find the new current. Now current will change because the total resistance has changed. So then I will be 500, V in divided by R total, right? Ohm's law. So this is 12 volt divided by 541. Now I'm going to change into 400, right? Kilo ohms to ohms. And that's going to be very little current, right? Almost in microamp. So that's the current. And then your new voltmeter reading, will be like this. So you have to be careful. I times effective R2 parallel R, right? Okay, because the voltmeter is sitting here at this branch, at this node, right? At this branch. So you have to put the effective resistance, right? Which is the parallel combination, between R2 and R. It's not just R2. You can't just do I times R2, because since the voltmeter resistance is sitting here, the new voltmeter reading will be I times the parallel combination. So you have to be a little careful. Okay, now you have everything. So 2.216 10 to the power negative 5, that's the new current, and its parallel combination is 1 over R2 plus 1 over R, right? Inverse. And then you can now you will have to, since we have calculated current in amps, you have to convert kilo ohms into ohms. R2 is 500,000 and the voltmeter resistance is 900,000. Do that, and then if you do, so new voltmeter reading, right? So the voltmeter reading will be 7.12 volt. If you do this calculation, this calculation, 7.12 volt. So what we know from theory, right, from mathematical equations, is supposed to read actually 8.33 volt, but because of voltmeter impedance, voltmeter internal resistance, right, comparable to this, right, it's just recording 7.12, and it's significant change actually, so you can't neglect it. So well, and this is called loading effect. It's a very important concept in electrical circuits. And what percentage is percentage difference. So you can say percentage difference in the reading, right, will be, so V actual, which is 8.33, minus V V voltmeter reading, right, divided by V voltmeter, no, actual. Okay, so this is 8.33 from part A minus 7.12 divided by 8.33, and in terms of percentage, this is going to be 14.5% off. So you can clearly see that because of the voltmeter loading effect of the voltmeter, you will read actually 14.5% off, right, than actual values. So I'm going to solve more similar questions before we start Kirchhoff's law complicated circuit. So here's the next question. It has two parts. So the circuit shown has two resistors connected in series, 36 ohms and 24 ohms, and the voltmeter is connected in across the 24 ohms, right? And the first question, what's the voltmeter reading when the switch is open? When the switch is open, right, then you have two resistors in series, right? And so it's easy, actually, a lot easier actually. So first find the total current. Total current is total voltage divided by R total, right? And you can right away calculate. It's 9 volts divided by R total is 36 plus 24, which is 9 over 60, right? And that's going to be, so calculate that, right? That amps, and then your voltmeter reading is just I times R2, right? So current is same 9 over 60 times R2 is 24 ohms because the voltmeter is connected across 24. So times R2 gives you the voltmeter reading, and that's going to give you 3.6 volts. Okay, this voltmeter right here, when the switch is open, right, will record 3.6 volts. So the next question is part B. I'm going to solve here. What's the voltmeter reading when the switch is closed? Okay, when the switch is closed, now the equivalent circuit is like this, right? It's very simple now. When the switch is closed, right, this is now bypassed, right? This is gone now. The first resistance is bypassed because the switch is closed, right? Switch is turned on. Now you can assume that, you can imagine that there's no R1. So you have only 24 effective resistance in the circuit. And this is the voltmeter resistor, voltmeter record. Now once the switch is closed, when switch is closed, it will bypass 36 ohms because you have, this is just conducting, right? And this is very easy now, right? So the new current is V over 24, right? Because the only resistance you have is 24. So 9 over 24, and the new voltmeter reading I times R2. So 9 over 24 divided times 24 is just 9 volts, and makes sense because the only resistor you have is this, and it should read the same 9 volt, right? And third, part C is now for second circuit, right? Now instead of switch, right, it says instead of switch you put 41 ohms of resistance in parallel with 36 ohms. So what's the new voltmeter reading? And this same thing. Now it will change the effective resistance. What's the R total, right, here? So R total And so here's the total current. It will also be same again, right? But it will change the effective resistance, and it will change the total current configuration in this configuration. So what's the R total is 36 ohms, right? Parallel, so I'm just gonna use symbol 41, right? Plus 24, right? There's 2 in parallel, which you can calculate, plus you add this, and parallel combination, right, is 1 over 36 plus 1 over 41 inverse plus 24, and that's the total effective resistance now. And if you do that, is 43.2 ohms, right? And then once you have the total effective resistance, the new total current is V over R effective total, right? So V is still 9 volt divided by 43. So that's your new current. It will change the current, total current through the circuit. Why? Because you have changed the effective resistance. So now this is your new current. So new current is 0.208 amps if you do this calculation. And so now what's the new voltmeter reading? Voltmeter reading I times R2, right? So 0.208 times 24, because you're looking because voltmeter is connected across 24, and it's acting the voltmeter reading. And if you do that, is 5 volts. So the voltmeter reads different voltage in different situations. So you have to understand this. Here's the next problem. Now we're gonna consider doing some Kirchhoff's laws application, starting with a very simple circuit, something like this. So you're given 2 batteries, 12 volts, 6 volt, and there are 3 resistors. It's asking what's the current in the circuit, and obviously there's no branch, right? Only single loop. The current has to be same everywhere. And so before you apply Kirchhoff's law, right? If you go back and see the rules, first, if the direction of the current is not given, you have to choose the direction of the current of your own. You can choose your own direction of current if it is not given. And even if the direction of the current is wrong, you will end up with negative current, so that's the most advantage, good part of Kirchhoff's law. You can choose the direction of the current of your own, and if it is wrong, then you will end up with negative current. The magnitude will be same. So the best case will be like this. So since this is 12 volt battery, this is 6 volt. 12 volt battery will try to push more. So I'm gonna choose the direction of the current counterclockwise for best case, or you could choose clockwise as well. And after that, what's the next? Next is putting all the polarities, plus and minus sign for all components. So battery, this is obvious, right? This is positive, negative. Since current flows in this direction, right? For this resistor, this has to be the positive part. This has to be the negative, right? Because conventional current always flows from higher to lower potential. Same thing, positive and negative. So back here, same thing. So current flows from here to here, right? So this side of the resistor must be at positive potential, and this side must be at lower potential, negative. So once you have that, then you choose the loop. So obviously, I'm gonna choose the counterclockwise loop, right? And apply, and then after that apply Kirchhoff's loop law. So Kirchhoff's voltage law said the sum of the voltage, right? Sum of the potential difference of voltage around any electrical loop must be 0. That's the Kirchhoff's second law, voltage law. And let's start with this. So 12 volt battery. So I'm going counterclockwise. So you're going from negative to positive. So this is positive 12 volt, right? And on the resistor, however, you're going from positive to negative. So the voltage potential difference across this resistor is negative. Negative current is unknown, which is what we're trying to figure out. 12, same thing, minus current is same in all 6. And then you're going from positive to negative. For the second battery, however, you're going from positive to negative. So negative 6 volt, right? And then finally, for the 8 ohm, again negative, because you're going from positive to negative. So I times 8 is equal to 0. So that's your Kirchhoff's voltage law around this loop, right? And so this is now this is just the calculation. 6 minus 24i, right, is equal to 0. So I is equal to 6 over 24, so 1/4, 24 amps. So that's your answer. right? So you get the current, positive current. That means the choice of current you choose is right, right? So if you now, if you choose the direction of the current in opposite clockwise current, you will end up with negative current. That means negative current means simply means that the direction of the current you have chosen is actually opposite to what the actual current is flowing through the circuit, but the magnitude will be exactly same. That's the most advantage, of using Kirchhoff's law. So here's the next problem. Again, we're gonna apply Kirchhoff's law. Here you're given this multi-loop circuits, with two batteries, three resistors, and this is the ammeter, current meter connected, and it's recording 3 amps. And it's asking three things. So what's the unknown currents, I1, I2, right? And what is the unknown battery voltage? So these are the questions it's asking. So again, now at this junction, I1 is coming, I2 is coming, and that means the current through this branch, right, must be going best case, right? Let's call I3. So I3 is actually 3 ohms, 3 amps, right? It has to be 3 amps because ammeter records the current I3. Okay, then you can choose. So first of all, at this junction, right? At the junction, this junction, right? This junction. Kirchhoff's current law says I1 plus I2 has to be I3, right? So I1 plus I3 is 3 amps, right? Which we're gonna use this relation later, actually. Now, first let's figure out I1 and I2. So, and in Kirchhoff's law, you can choose any loop you want, right? You can pick any loop you want, and so first I'm gonna choose the left hand loop, the first left hand root, and I will go the clockwise direction. So put positive, negative, since this is positive, right? Because since current in this resistor flows this way, positive, and on current on this is this, right? And current here on this is positive, negative, positive. Okay, so choosing the first half loop. So I'm going to apply Kirchhoff's voltage law in the first half loop. So when you choose first half loop, forget the rest of the circuit, right? So you can just ignore the rest of the circuit and apply Kirchhoff's voltage law around this loop. So again, the sum of the voltage has to be 0, right? And starting from the battery voltage, I will start from 9 volts. So positive 9 volt, right? And here again is the voltage across 3 ohm resistor has to be negative because you're going from positive to negative, right? Negative. I1 is the current, 3 ohm is the resistance, and now since I'm just taking the first half loop, so now the next is this resistor, 2 ohm resistor, again negative, but current here, remember, is not I1, current here is I3, we call it I3, which is 3 amp, right? So I3 times I3 times 2, right, 2 ohms is equal to 0, the 3 voltages, and then solve for I1 because I3 is given. So 9 minus this is 3I1 minus I3 is 3 amp, that's given. So this is 6, 3 minus 3I1 is 0. So that gives you I1 is 1 amp, right? So I1 is 1 amp. Then from this relation, since I3 is 3 amp, I'm sorry, this is I2. Okay. So since you're given, we have already calculated I1, then you can solve for I2. So from equation number 1, right, I1 plus I2 is 3 amp. So then you can right away you can calculate I2. I2 is 3 minus I1, which is 3 minus 1 is 2 amp. Okay, so we have calculated two unknowns. I1, we have calculated I1, I2, right? We still need to figure out this unknown battery voltage. And then to do that, obviously you use the left hand, right hand loop, right? This loop, and I'm going counterclockwise. So just forget this, and you use Kirchhoff's voltage law around this loop, right? and find out that. So I'm going to do it here. Kirchhoff's voltage law, choosing the second half loop as shown. So sum of the voltage around the second half loop is 0. So I will be starting with the battery voltage, right? I will starting battery voltage is positive EMF of the battery, right? and negative I2 times 4.5, again negative I3 times 2 is equal to 0. So E minus I2, we have already solved for I2, 2 amps, 4.5. I3 is given 3 amp, and that's your EMF. So 9 plus 6, 15 volt. So the voltage of this unknown battery, has to be 15 volt in this configuration. So that's how you apply Kirchhoff's law. Okay, here's the next similar question, but with more unknown quantities, and it's a perfect way to apply Kirchhoff's law. If you have no more unknown quantities, it's best to use Kirchhoff's law. Okay, here's the circuit again. You have two batteries, right? And these are the resistors, and these are the currents given. Even if the current direction of the currents are not given to you, and you could choose the direction of your own, but the direction of the current. So it's acting this all unknown currents, I1, I2, and I3, all unknown currents, right? So first of all, just to begin with, at this junction, I1 plus I2 is equal to I3, right? That's and then we might have to use that later, right? Okay, let's call equation number 1, right? So then next we're gonna again first put all the positive and negatives, positive side, negative side, positive side, negative side, positive side, negative side, right? Okay, so I'm gonna use this loop. So on this loop, choosing this loop, the sum of the voltage right around that loop has to be 0, Kirchhoff's voltage law. And then let's apply then voltage law. So it's starting from so positive 12 volt minus I1 times 3.9 minus I3 times 1.2, right, is equal to 0. So this can be written as 3.9 I1 plus plus I2 has no coefficient, right? So I2 0 I2, right, because I2 has no coefficient, and plus 1.2 I3 is equal to 12, right? Because I just shifted. Let's call equation number 2. And now this loop, the right hand loop, second half loop, I'm gonna go this way. You could go this way or that way, doesn't really matter. So that loop, second half loop, gives you same, right? So let's apply voltage law across the second half loop. That's going to get you 9 volts, positive 9 volt, right? Minus I2 times 6.7 minus I3 times 1.2 is equal to 0, right? And now do the same thing. You're gonna do since you don't have I1, so 0 times I1, because the coefficient of 0 is coefficient of I1 is 0, plus 6.7 I2 plus 1.2 I3 is equal to 9, right? Okay, since you have 3 unknowns, I1, I2, I3, we saw 3 equations. So this is like, you could actually reduce to 2 unknown, because you know the relationship between I1, I2, I3, but you can directly do this actually. Since you have 3 unknowns, you'll have 3 unknown equations, 3 equations. So it's a 3 unknown, 3 equations type of problem, or 2 equations, 2 unknown type of problem. And you can put them in the standard way in electrical, in engineering is actually a circuit problem is put them in a matrix form, and solve it, numerically or using calculator or using computationally, that would be a lot easier. That's the standard technique. So let me show you, or you can solve it, manually. So using from from equations 1, 2 and 3, put them in matrix form, you know. So it has all coefficient. The coefficient of I1 is 1, right? 1, negative 1, 0. So something like, you can put them in matrix form, something like that. See, 1, 1, negative 1. So from second equation, you have 3.9 coefficient, 0, 1.2, right? Third equation, 0, 6.7, 1.2. So you have this, and the unknown quantity I1, I2, I3 are your unknown. And right hand side is your coefficient 0, second is 12, and third is 9, right? So you can put them in matrix form like this, right? Linear algebra. This is all about. That's the main applications. Because if you open this, right? See here, if you open this, if you open this matrix, you're gonna get these three equations. So it's just summarizing this. This basically summarizes the three equations, and solve it. You know, solve it using a calculator. So figure that out, how to calculate this, or using Python or computational, you know, computational using Python and any other program, and solve it. And then if you solve it, you know, so to figure out how to calculate the matrix, right, like this, you know, using calculator, that would be a lot easier for you. And so if you do that, so answer, I'm just gonna write on that. So calculation part using calculator matrix, you know, I'll leave it up to you. 5.13 amps and 2.97 I3. Okay, so these are the answers. So this is a standard way of solving, you know, circuit problems like that. So if you have three unknowns, you'll have three equations and put them in matrix form, right, and then solve them like this. Okay, here's the next problem. Again, you might need Kirchhoff's law to solve this problem. Here's the question. So these are the circuit, 2 batteries, 3 resistors, and the switch is here, right here. This is the switch symbol. And first question is, what's the current, you know, through each resistors, right, when the switch is on. So when the switch is on, right, when the switch is on, so what's the, so first, since the direction of the current is not given, you have to first best guess the direction of the current. You can choose any direction you want. So I will just do it like this. This battery will send current, let's say I1, right, and this battery will send, let's say I2, and then they will both come down as I3. So that's my best case, right? You can choose any direction you want. And since direction of the current, based on the direction of the current you choose, you have to put the positive and negative sign. Since this flowing current goes from this way, this side is positive, this side is negative, same thing, right? And since, but here current goes down, so the direction of positive and negative is right here, because current goes like this, right? Okay, so first of all, at this junction, right, at this junction, Kirchhoff's current law says I1 plus I2 has to be I3, common sense, right? That which we are going to use later again. Now again, I'm going to use the first half loop. This loop gives you what? Again, exactly same technique. So here your current is I1, right? So but you're starting from here, so you're going from positive to negative. So negative I1 times 10, that's the voltage across 10 ohm. The voltage of the battery is positive, however, because you're going from negative to positive. Positive 10 volt, right? And back to here. So this battery, 15 volt battery, is negative because you're going from, because we're choosing this loop, right? We're going clockwise. So this battery voltage is, you know, this battery voltage is negative because you're going from positive to negative. So 15 volt. And back to this resistor, right? Since your loop, we're going, yeah, once you choose this loop, you always need to follow this, right? So since you're going, your loop current that you choose is like this, right? So but you're going from negative to positive, right? See here, you're going from negative to positive. So this is positive. The current here is I2. So I2 times 8 ohms. So that's your Kirchhoff's voltage law. Okay. around that loop. And then you do some simplification. So 10 I1 minus 8 A2 is negative 5, right? Yep, equation number 2. And now one more loop left, right? Which is this. So let's choose this loop. So this loop will, again, some of the voltage around that loop is 0. So starting with 15 volt, positive 15 volt, because you're going from negative to positive, and going down, you always follow this loop, right? Since we're going like this, so you're going from positive to negative. So it's negative, current here is I3 times 4, and back here again, since you're going from like this, so you're going from positive to negative. So negative I2 times 8, so only 3 voltage, that is equal to 0. So you're going to get the relationship between I2 and I3. So that's going to get to so what you're going to get, 8 I2 plus 4 I3 is equal to 15, right? And you can again do the same thing. Actually, you can either reduce these 3 unknowns to 2 unknowns, because you know the relationship between the relationship between I1, I2, I3, because I3 8 I2 plus 4, I3 is I1 plus I2, right, from equation number 1 is 15. Now if you simplify that's gonna reduce the variables into I1 and I2. So 4 I1 plus 12 I2 is equal to 15. Okay, so after simplification, equation number. Now this is now using these two equations have I1 and I2 variables, right? So using 2 and 3, you can write down the coefficients or solve 2 unknowns, 2 equations, whatever way you want. So 10, negative 8, 4, 12. So I'm just going to put it in matrix form, and the variables are I1 and I2. The right hand side is negative 5 and 15. Because if you open this matrix, you're going to get equations 2 and 3. And solve it using, like I said, using a calculator. So learn how to use the matrix. Or computationally, and you'll get these answers. So I1 is 0.39 amps and I2 is 1.12. Or you can just use whatever way you want, how to solve 2 equations, 2 unknowns, right? Okay, so that's the first part. Now second part says determine the magnitude of the current that flows through this, right? I1 and I2 when the switch is open. Now when the switch is open, right, back to this figure, when the switch is open, this third resistor, this is gone, right? So when the switch is open, then here's the equivalent circuit. So you have now only this equivalent circuit, right? Because when the switch is open, you have only single loop, and that makes it a lot easier, Okay, you have only single loop, right? Everything is in series, so current has to be same everywhere, right? Current has to be same everywhere, and you just pick the loop, so the best guess is actually, since this is 15 volt, this is voltage is more than that, the best case is actually this, right? Or you can choose, so you just go like this. So 15 volts minus, this will be minus now because you're going from positive to negative. 10 volts, and this is positive, negative, right? And here you're going from that way, so negative, positive. Okay, minus I times 10, and here again minus I times 8 is equal to, and then this 5 minus 18I is equal to 0. And then I is 5 over 18, and that's 0.28 amps, right? Okay, that's how you solve when the switch is open, the current is entirely different. Here's the next problems on electric bulbs connections. So it's given 3 electric bulbs, different wattage, connected in like this, and 120 volt bulb battery is connected, and it's acting. So it's acting the current through each bulb and the power, the power rating of each bulb was the, and it's acting which bulb burns brighter, which one will have the most intensity. So first, don't get confused. This what is so the manufacturers will give you the specification for each bulb. So whenever it says 120 volt 40 watt bulb, right, it simply says if you put 120 volt, it's going to give you a maximum of 40 watts. That's the maximum power rating. Okay. So if it says 120 volt and 20 watts, that simply means if you put 120 volts, it's going to give you 20 watts. So obviously, so these bulbs will not be will not be burning at its full rate. Because why? Because it's not getting 120 volts, because they are in series and parallel, and the voltage will be divided, right? So then, since they are not getting the full voltage 120 volts, so they will not shine with burn with the full wattage that's specified with the manufacturers. So we need to figure out what's the actual power rating for each bulb, and to find that, first we have to find the current through each bulb, and you have to treat them as resistor. So first, each bulb is equivalent to a resistor, because it has a filament right inside it, and then it's basically a resistor. So you have to first figure out the equivalent resistor. So to find the resistance, you have to use manufacturer specification. That's what it says, right? To find because resistance of the given bulb is constant, it doesn't change, right? So to find the resistance, you have to. So let's first figure out the resistance. So each bulb then each bulb can be converted to resistor, right? Equivalent resistor, because each bulb has a filament, and it's. So first question we're solving when the switch is open. When the switch is open, you have all these 3 bulbs in circuit. So this first bulb is replaced by a resistor R1, which we need to figure out, and then you have bulb number 2 resistor and R2, R3, and that's the circuit, right? So let's call R1, R2, R3. So first, our job is to figure out this R1, R2, and R3. All the resistances, right? And this is I1, right? And I1 obviously gets divided into I2 and I3, right? Which we need to figure out using Kirchhoff's law again. So how do you find R1, R2, R3? So it says use manufacturer specification. You must use the manufacturer's specification, right, to find the resistance of each bulb. So that's our first job. Okay. So first job is to find manufacturer specification, and it says so since power is V square over R, right, that's the relationship between power, voltage, and resistance. So resistance R1 is V square over power P1, right? V is same. So manufacturer specification, when you put 120 volt, you get 40 watt max. So 120 volt is same for all. Power P1, since we are finding R1, power P 40 watts, right? That's going to get you that's going to 360 ohms if you do. Similarly, R2 is 120 volts square and 20 watts, and that's going to give you 720 ohms. And R3 is R3 is 120 square over 60 watts, and that's going to get you 240 ohms. So that's the first part. The first part is just action. What's the equivalent resistance of the filament of each bulb, right? And then you can just, after finding this resistance, you can just convert them back to the simple our circuit problem, right? Because bulb is replaced by resistors like this, and then you can use Kirchhoff's law or series parallel, whatever you want, and then solve the usual. So our job is to figure out I1, I2, and I3, the current through each branch, and because once you have current through each branch, then you can find out the power rating, the actual power rating, right? So that's the next part, so part B is to figure out the actual power rating for each bulb. To find that out, so first you need to figure out the actual current through each bulb, and then which we're going to solve. So now I'm going to solve part B. It's asking the actual power rating for each bulb. So our job is to find this unknown currents. So let me write down the circuit one more time again. So you have 120 volt bulb and the first bulb, right, and then the second bulb and the third electric bulb. They are all now converted back to resistance, and we have already calculated all these resistances, right? So this is I1, which is now will be divided into I2 and I3, right? And this is and based on the direction of the current, this side of the resistor is positive, negative, positive, negative, positive, negative, to apply Kirchhoff's law. So let's find out I1, I2, I3 using Kirchhoff's law, because that's the easiest way to solve problem, right? So first of all, at this junction, right, so I1 has to be I1, I2 plus I3, obviously. Kirchhoff's current law. Total current entering must be total current leaving, which we're going to use later. Okay, now next is this loop. I'm going to use this loop, the first half loop, right? I can choose any loop. So once you choose this loop, just right now for a moment, forget this part, right? And apply Kirchhoff's voltage law. V is 0. So starting from 120 volt plus 120 volts minus I1 times R1 minus I2 times R2. Right, and put all the numbers because we know all the resistance values. So I1 times R1 is 360 minus I2, the R2 is 720, is equal to 0. So let's call equation number 1, let's call equation number 2. And now this loop, right, because you have different loop here. So forgetting R2, so again sum of the voltage around that loop is 0, right, this loop. So 120 volts minus I1 R1 minus I3 R3 is equal to 0, right? So 120 minus I1 R1 is 360 minus I3 can be written as from here I3 is I1 minus I2, right, because we want to convert 3 unknowns to 2 unknown variable, or you can just write down all 3 unknowns in a matrix form and solve all the 3 unknown right away. You can just first reduce 3 unknowns to 2 unknowns, whatever way you want. Okay, minus I1 360 minus I1 minus I2 R3 is 240, and simplifying that will give you will give you 120 minus 600 I1 plus 240 I2 is. So now just solve 2 and 3, because equations 2 and 3 are have I1 and I2, right, unknowns, right? You have 2. Now this is now has reduced to 2 unknowns, 2 equations. You can put it in matrix form, or you can put it in just right away. You can, so 360 I1 plus 720 I2 is equal to 120, right? That's your, before you put into matrix form, so that's going to give you 600 I1 minus 240 I2 is equal to this, right? And in matrix form, or just solve whatever way you like. Matrix form, if you have more and more unknown variables, big matrix, then it's easy to solve in matrix form, because the calculator can solve the matrix, right? 360 720, and you just need to write down the coefficients, right? And this is the variables are this first one 120, both 120 120, okay, right? And solve the matrix. using calculator or using Python or using any computational method. So just search it, how to solve the matrix. And this is just 2 by 2 matrix, right? And then if you solve it, so I1 is going to 0.222 amps, I2 is 0.0555 amps, and I3 is just from equation number 1, I1 minus I2, and that's going to give you 0.166 amp. Okay, so we have figured out, right, these three unknown current. Then you're done. So then you can find out the actual power ratings. So now, because that's what it's asking, which bulbs will burn with the brightest intensity. So to find out, you have to, because brightness is proportional to the power rating, actual power. So that's why we're doing actually. So P1 is I1 square R1, right? And I 0.2, that's the reason we have found the actual current. So R1 360, and P1 is 17.7 watts. Okay, so similar, P2 is I2 square R2, so figure that out again, right? And then 2.22 watts, and P3 is I3 square R3, and figure that out, 6.7 watts. And just by comparing this power, these are the actual power ratings actually, right? And just by comparing this to so which because the question was actually which bulb burns brighter, right? So you can clearly see, right, the first bulb, this first 40 watt indicated by this, right? This bulb will burn with the brightest intensity because it has more power rating. And then third, so you can do P1 is greater than P3 is greater than P2. Okay, so that's how you solve bulb problem like that. So note that, don't get confused, they won't burn with as specified by the manufacturers, because the manufacturer wattage works only when they get 120 volt, and since with this connection they are not getting 120 volt, right? Okay, so that's how you solve the problem, something like that. So here's the next question, is just conceptual, So here now it's asking again, figure out the power ratings, which bulbs will burn with the brightest intensity when the switch is closed now. So when the switch is closed, right, so what is the equivalent? When the switch is closed like this is gone, it will bypass, right, it will provide a short circuit path for the P1, right, this R1. Now this will provide a jumper, right? You are just putting a jumper, so it will just ignore, right? Now you can just ignore the first bulb. Now what you have is just two bulbs like this, right? And they are equivalent to a resistor. The resistance is same, R's are same, right? Resistance of the bulb don't change, they are fixed. So this is R2, and this is very easy actually. You can do the calculations, again, same thing, Kirchhoff's law or series parallel. But here R2 and R3 here, right, they are in R2 and R3 bulbs, right? They are the equivalent resistors, are in parallel with 120 volt battery, right? So that means based on the manufacturer specification, we already know that, but they will burn with the full power, right? So then P2 will be 20 watts, P3 will burn with 60 watts. So P3 will be brightest, right? And P1 will be 0, right? You can test it actually in lab, because this will not turn on at all. P1 will not turn on because it's short circuited. Okay, that's it. So they will burn with full power now. Why? Because they are getting the 120 volts, and based on the manufacturers, when you put 120 volt, right, they will get you 20 watt, and when you put 120 volt, this will get you actual 60 watt. Or you can just try it actually. You can just try by doing the actual numerical problems, just first figure out the I1 and I2, I2 and I3, right? Just by using the same circuit problems, and do I square R, I3 square R3, and you will find out that they will have the exactly same power, okay. So our last topic is the RC circuit. RC, is the capacitor charging and discharging circuit. And first, make sure to read the lecture. Watch the lecture video. Okay, here's the charging and discharging circuit. So first, this capacitor is connected to the battery side. So this is a two-way connection switch, right? So first, the switch is connected to the A, which will charge the capacitor, right? It will fully charge the capacitor. Right, first it says it's connected to like this for a long time, right, to the 9-volt battery. The capacitor is fully charged. The first question is, so it's asking what's the charge on the capacitor, charge and current in the capacitor, right? First question is immediately after the switch is closed. So first question is really easy, right? So first, what's the voltage? Since it's fully charged, in the beginning the capacitor is fully charged, the voltage across the capacitor is just the 9 volt, right? Because it's connected to the 9-volt battery for a long time. It's fully charged. So then Q is, right, initial is just CV, right? That's the capacitor relation. So capacitor is 2 microfarad, micro means -6, and voltage is 9. So 18, right? Microcoulombs. So you can just keep it in microcoulomb like that. So that's the initial voltage, okay, initial charge on the capacitor. So the initial current is, you don't need this. Initial current is acting, you throw that switch to the B, right, and it's acting immediately after the switch is closed. This side, what's the current? So current in the beginning will be maximum, and maximum current, right, is just V voltage across the capacitor over R, and initial voltage across the capacitor is just 9 volt, right? It has full voltage. Divided by resistor is 50, and that's it. So that's the initial current, 9 divided by 50, so 0.18 amp, right? Okay, next question is at 50. So once you switch that here, right, now first fully charged, and then after that you throw that switch to the point B and it will discharge, right, like this. So it's acting at, after time is 50 microseconds, right, what's the charge remaining, right, and what's the current? It's acting current and charge on the capacitor, right, through the circuit at 50 microseconds, and then you can now just use now it's a discharging, right? So check the formula, it will discharge exponentially, right? So if you check, so this is a charge and current, right, it will discharge like this, right? We know that. And Q naught is the initial charge, which is this 18 microcoulombs, right? You can just put it in microcoulombs, and then you just do T as T is this, T is 550, because we're looking at the charge after 50 microseconds. So 50 micro means 10 to the power -6 divided by resistance is 50, and capacitance is 2 10 to the power -6. So that's the charge after 50 microseconds, after turning the switch to point B. And then you can just do this calculation, right, and then 10.9 microcoulombs, right? And what's the current? So current will also decay exponentially, and this is the formula, right? Exactly. So I naught is the initial current, which is 0.18 amps. Negative time is 50 micro divided by R is 50, and capacitance is 2 micro. So that's the current, 109 amp. The current will be this, and they will further reduce exponentially with time. You can try after at t 200 microseconds to do the exactly same process. So similar problem again. So you're given a discharging data. This is a capacitor is discharged through a resistor, and it will discharge is you're given the data. The time axis, however, is in millisecond, and this is in volts. So the capacitor used in this experiment, it says a 50 microfarad capacitor is discharged, and the initial voltage, right? The initial voltage across the, which is the full voltage when the capacitor is fully charged, is 30 volt. And what is the value of the time constant? So first question is, it has two questions. First question, what's the time constant, right, of the circuit? Second question is, what's the resistance used in this experiment, right? So that's the two things. So time constant and the resistance, right? So then back to the data. So go back to the, so you have to pick the voltage of the instantaneous voltage of the capacitor at given particular time. So choose the time where you exactly know the voltage. So the best would be this, right? Best would be at 2 milliseconds, because at 2 milliseconds, right, you exactly know the voltage across the capacitor is 10 volts. So you could pick any time actually you want. It doesn't really matter. At t is 2 milliseconds, which is to make sure to convert into seconds. What's the voltage across the capacitor? The instantaneous voltage across the capacitor is 10 volt, right? And based on that, what's the, then just use, so this is a discharging, right? And go back and check the formula for discharge. So voltage across the capacitor discharges like this. V is V max, which is V naught in V max, which is 30 volts initial voltage, right? And it will discharge. It will decrease exponentially with time, right? Tau is RC, so this is R tau. This is what we're solving, and then just do some log algebra. So this is 30 volt. This is 10 volt. That's the instantaneous. Initial. This is the max peak voltage, which is 30 volt. E minus tau. So the time we are looking at 2 milliseconds, right, by tau. So this, just divide both sides by 30, is going to give you 1/3 is E minus 2 10 to the power negative 3 over. Now how do you get rid of the exponent? Then you have to take the natural log both sides, right? If you take natural log ln in your calculator, and this is gone, so whatever left is this coefficient, is the exponent power. That's it. And then you solve for tau, which is the time constant of the given circuit, and make sure to read the lecture about time constant. What's the physical meaning of time constant? And you can just this negative, but log of 1/3 will also give you negative value, right? And negative will give you the positive time constant. And if you do that, so the time constant for this circuit will be about 0.0018 seconds, or you can convert into millisecond if you want. 1.8 milliseconds is the time constant. So time constant, basically the physical meaning is it takes this much time to discharge by 63%. That's what the time constant is. Okay, second question is, what's the resistance? Now once time, the other formula of the time constant formula is RC, right? So the capacitance is given, so R will be time constant divided by C, right? So the resistance will be this. Time constant is 0.0018. So capacitance is 50 microfarad, right? So that's your resistance. So the resistance of this resistor used in this experiment, in this discharging process, is 36 ohms. So here's the last question, and this circuit is used for the camera flash unit. Your camera flash unit for flash system, you use the circuit something like. It has two switches, S1 and S2. S1 is used for charging the capacitor. This is your charging capacitor, big capacitor, and this S2 is used for flash. So once the capacitor is fully charged, when you turn this on with this off, then it will dump all the energy through this flash system. So this is particular. Okay, so here is just simply the question is very easy. So you're just charging actually. So okay, so it says how long does it take to charge the capacitor to 8 volt? Okay, the maximum volt is 10 volt, right? Because that's the battery voltage. This is the resistance in the system, and the capacitance is 100 volts. It's asking how long does it take to charge the capacitor to 8 volt? So here's the data. So you have maximum volt, V naught, right? Maximum is the V battery, right? The maximum voltage it can be charged is the battery voltage is 10 volt. And what's the instantaneous voltage? VC is you want to charge at because you are figuring out how much time it takes to charge by 8 volt, charge up to 8 volt. That's what it is. So R is 40 kilo ohms, 40,000. Capacitance is 120 micro farad, right? And this is a charge. It's asking how long it takes to charge. So charging formula. So charging formula, if you go back and see, VC is V naught 1 minus ET over RC, right? Or this is RC is just the tau, it's time constant. Okay, and then you solve for tau. So just put all the values. So VC is 8 volt. That's the instantaneous voltage. V naught is always maximum. It's a 10 volt battery voltage. 1 minus E time. We're solving how long it takes. So we're solving the time big small t. We're solving this time. So R is 40,000 times 120 10 to the power negative 6. So that's gonna. So first divide by both sides by 10, right? And then you just solve it the way you want, whatever way you want. Okay, is 1 minus e to the power negative by 40,000 times 120 10 to the power negative 6, right? And that's going to give you 1 minus 8 over 10. I'm just simplifying the algebra. You can solve it on your own, right? And this is going to get you what? So 1 negative 8 over 10 is 0.2 is and then talk. So the next step is to, of course, take the natural log, right? Is now becomes this, right? And solve for t. And if you solve for t, is 7.72 seconds. So it's gonna take about 7 seconds or 8 seconds to charge it up to 8 volts.